My name's Callum Court, and I'm a PhD student here at the University of Cambridge in the Department of Physics with Molecular Engineering. And I'm going to talk today about ChemDataExtractor, which is a toolkit for automatically extracting chemical records from scientific documents for the purpose of generating databases of materials properties in a completely automated way. So I'll just give a brief introduction now of all the sort of ideas of text and data mining, things we've heard about today. I'll then have a quick overview of some of the previous work that's been done in large-scale data mining for materials discovery. From there, hopefully, we'll sort of begin to understand the real challenges that you face from actually extracting information from scientific documents, in particular, the chemistry literature. I'll then go on to give a complete overview of how the ChemDataExtractor toolkit hopefully solves some of those problems. And from there, I'll go through applications and some of the current work we're working on towards improving ChemDataExtractor even further. So to sort of set the scene, something we've heard a bit about today already is that there's approximately 20,000 new compounds and properties published in approximately 10,000 chemistry journals every year. And so if we extrapolate that out to the wider fields of material science, we see that there's this vast, ever-growing corpus of scientific data that's becoming harder and harder for researchers to keep up to date with all the progress that's happening in their field. In an ideal world, all the data that we publish would be available in some kind of easy-to-access database where we could quickly find what's been done in our field with no real trouble. But of course, as we've seen, creating a database of that kind manually by going through papers, extracting data, and uploading it to a database would be massively time-consuming, massively expensive, and actually, despite sort of popular opinion, it would actually be quite error-prone as well. So we know that scientific results are typically published in papers, patents, and theses, and these are typically semi-structured documents. They always follow a similar sort of format with an abstract, textual elements, and figures, schemes, tables, and captions. But these elements are not easily readable by machines for a number of reasons. But it actually means that in order to extract information from a scientific document, we need to rely on machine learning techniques and natural language processing, which can then give us the opportunity to extract information and produce these databases. So large-scale data mining for materials discovery, although relatively new, has been quite extensively studied by a few initiatives and projects. So it's kind of paved the way by the Materials Genome Initiative, which led to the two big projects, the Harvard Clean Energy Project, which looked at trying to discover new materials for organic photovoltaic solar cells, and the Materials Project, which did a very similar thing, but looking at battery materials in particular. And they had a relatively large amount of success. The text mining tools for the chemistry domain vary from chemical tagger, which Peter Murray-Russ talked about this morning, and the ChemX project, which was kind of, as far as I understand it, an extension to the chemical tagger project. Now, all these previous projects tend to focus on applying data mining and materials discovery to a specific domain of science, a specific subdomain such as photovoltaics. And there's no issue with that, but these would all be very well complemented by being able to quickly, automatically generate databases of materials properties so that you can apply your data science research to a giant database of material properties and then go on to do things like materials prediction. Of course, what we'd like is a way to generate those databases in a completely domain-independent way. So whether you're in physics, nanotechnology, chemistry, biology, you can generate a database of materials using, hopefully, the same tool. Now, despite what I said about there being some relative structure to scientific documents, there are a few issues with trying to extract information from scientific papers. And the primary one is that we require some extent an expert knowledge in order to understand a scientific article. And this comes in the form of things like terminology and abbreviations that are completely domain-specific, but may appear in other domains of science. The classic example I always use is DFT, which in chemistry, well, chemistry and physics, but someone might say it stands for discrete Fourier transform. Another person would maybe say that stands for density functional theory. And without some element of expert knowledge or understanding of the context of the paper, that might be difficult to interpret if you just see DFT written in a scientific paper. And we also have the problem, particularly in science, that our conventions aren't particularly rigorous. We tend to have slightly different conventions for labeling and naming conventions of compounds, for example, in different subdomains of science. The second point is that within a single document, with all the information spread out across multiple sections, you need to have a sort of understanding of context to be able to understand which parts of information are relevant to which compounds or which even, well, anything that you're talking about. For example, a title of a paper may contain the compound that you're talking about in total, but the sentences below, if you were to read them individually, would not give you any indication of which compound you were talking about. And so there needs to be some level of interdependency resolution if we want to produce very well structured and very high precision databases of materials properties. So hopefully that sort of motivates why we need a tool like ChemDataExtractor, which is a comprehensive toolkit for automated extraction of chemical information from scientific documents. What that means is that given scientific papers, we can extract things like melting points, absorption spectra, glass transition temperatures, and many more chemistry properties, and in a way that it's completely structured and suitable to be placed into a database. As a side note, full source code, documentation, all available completely open source on ChemDataExtractor.org. There is also an online demo if you want to go and have a play with it and see how it performs. Particularly works very well in the chemistry domain, and it does work well with other domains as well, but it's definitely worth playing around with if you're interested. But now the key thing is, how does it work? So this is a general overview of how ChemDataExtractor works. So we start, I'll go into more detail with each block in the coming slides, but the kind of idea, we start off with a paper or thesis or patent in PDF, HTML, or XML. We pass through this sort of natural language processing pipeline, and what we get out at the end is a database of chemical records. So the first stage is this document processing. So as we've sort of seen, the different formats of scientific documents mean that we need to treat the way in which we process each document has to be slightly different. So what we aim to do in this first stage is to convert any type of document into a single consistent structure of elements. So as you can see, the textual elements get converted into these single ideas of being either paragraphs, sentences, captions, or maybe the abstract titles and headings, for example. And the tables get portioned off, and so do figures and schemes. They all get separated into different sections. And what we end up with, once we've removed unnecessary formatting and we've removed all sort of extra bits that you get with these typical HTML and XML documents in particular, is you end up with a nice consistent set of elements that is all very, say, object-orientated. We have a very clear set of each type of element and what to do next. So the textual elements go through this natural language processor, which is primarily the key stage of ChemDataExtractor. It's all about how do we extract information from text. And there's kind of 5 subparts: tokenization, part-of-speech tagging, entity recognition, phrase parsing, and information extraction. And that's probably best shown with a diagram. So I don't know if you can see, but at the top we have a sentence. Figure 2 shows the UV vis absorption spectra of 3A red and 3B blue in acetonitrile. So the aim of this stage is to extract information from the sentence. So the first thing we do is tokenize the sentence, split it down into individual tokens roughly corresponding to individual words. We then, that's a relatively straightforward process. The next stage is to tag each token with its role corresponding to what it does in sort of semantic prose. And so we identify nouns, we identify verbs, determinants, all these kind of things. And this is quite a famous process in natural language processing, and it's been quite well studied. But that enables us to perform the next stage, which is entity recognition. And this comes back to what I was saying about the challenges of text and data mining from chemistry, that we need to, at this stage is where we need to identify domain-specific terminology, abbreviations, and named entities. So here is where we recognize what compound names are, so for example, identifying that 3A and 3B are referring to chemical labels rather than some other figure or table within the document. And all these kind of entities, we say named entities, have to be recognized, including things like property identifiers, for example. And so once we've recognized those entities via a combination of machine learning processes, comparison to chemistry dictionaries, all these there's various different methods we can use. We do what's called phrase parsing. So the phrase parsing and information extraction go hand in hand. That converts the sentence into a tree structure. So like we can see, the overall topic of the sentence is a figure. It gets split down into its label and its type. 2, it's a spectrum. That, of course, has a subtype, UV vis absorption. We identify the two chemical labels and, as well, the solvent. So I'll come back to the bottom part with the interdependency resolution very shortly. But you can see that from there, it's very easy to extract relevant information from a tree structure. We know the type, we can find the label very easily, we can find which compounds it's referring to. Tables are more ideal to process. They're already in a semi-database format, so all we have to do is extract the information in the correct way, i.e. identifying which columns and rows mean identified to which parts of the headers. So we essentially treat tables in much the same way, converting them into this tree structure, just treating them as sort of highly condensed text. So the headings get found, so you might find a melting point in the header, you'll find compounds in the various rows, and you can easily extract the units and the values from there relatively easily. So at the end of this stage, what we have is that each element of the document has contributed a set of chemical records. So that's chemical names with associated properties, their values, and their units. Or if they are spectra, they might have the type of spectrum and the various solvents and things like this. We then have to do the key stage, which I was talking about earlier, which is the interdependency resolution. So again, the challenge was that we can't easily infer context from sentence-level processing. So what we have to do is look at higher and higher levels of context to be able to resolve the interdependency in a document. So what we do is, for example, we look for duplicate records. If we find two records with identical compounds and identical properties, we can delete one of them. If we find two compounds with different measurement properties, we can combine them. The most important stage is that if we find a record that's incomplete, for example, it doesn't have a chemical compound identifier, we can look at the latest section heading and say, was there a compound given in the section heading? If there was, we can associate it to that chemical record, and so on and so on. And that interdependency resolution enables us to build a sort of single set of consistent records that can then go into a database. The key point everyone wants to know is how good is it? How well does it perform? Well, to do an evaluation, we have to generate a sort of gold standard database. We take 50 randomly chosen articles from Elsevier, Royal Society of Chemistry, and the American Chemical Society, and we read them manually, we extract all the chemical records, and we create this gold standard. We then compare that to the ChemDataExtractor produced database, and we evaluate in terms of 3 metrics: precision, recall, and F-score. So precision being the fraction of correct retrieved results in the ChemDataExtractor database, recall being the fraction of the total number of gold standard records that we actually retrieve, and F-score being a kind of harmonic mean that enables us to get a sort of baseline measure so we can compare different methods. So the results are given in that table, the key line being the bottom line, which is for the total chemical property records, we achieve a precision of something like 94%, which means 94% of the records we retrieve are correct, which is really quite high. We did a very brief look at some manually curated databases, and they weren't an awful lot higher precision than that. The recall, slightly lower at 90%, roughly, meaning that we only find 90% of the records in a document, but when creating a database, we want to convince researchers that we're more worried about precision. We want them to be sure that the records they're getting in their database are correct, rather than having complete coverage in the database. And that yields an F-score of 91.5%, which is, considering there aren't any tools that do this complete process quite as comprehensively in the same way, it's hard to compare that to any other routines. But if you break that down into its natural language processing components and the various other components of the toolkit, it's comparable, if not better, in most cases than any other tool. So what can we do with these databases once we create them? Well, there's so many things. The primary one that's been done already is sort of trying to do materials discovery, property prediction, and compound identification. But the key, well, I think, is in research design, which, as we sort of touched on previously, it's meaning that researchers don't have to go through 30, 40 papers of previous literature to try and understand what has been done in the field and what to do next. They don't have to try and find the one review paper that gives a comprehensive overview. They can quickly check what's been done with certain compounds, quickly check what values we have for various compounds as well, and from there, we can understand where to go next and avoid repeating research, which is something that Peter touched on in his talk. So that kind of brings me on to where we are currently with this. My personal role in this project is to try and improve ChemDataExtractor's performance when we apply it to the physics literature, which has a lot of variation compared to the chemistry literature. There's less rigor in the way that the documents are structured. And the overall goal will be to create the first auto-generated database of magnetic material properties, which will hopefully have a lot of use in data storage, materials discovery, this kind of thing. So the thing to know about ChemDataExtractor is that this way in which we extract relations from text is based on rule-based programming, so kind of a dictionary of pre-programmed rules that have been programmed by effectively experts, have been designed to extract information from the various textual elements. But that's very time-consuming, so if you want to enhance ChemDataExtractor to find a new property, then you'll have to go in, add some rules yourself, try it out, and adapt the rules through almost trial and error, which is not the most efficient way of doing it. Instead, I'm currently working on implementing this snowball algorithm, which is a kind of a semi-supervised machine learning algorithm for relationship extraction. I won't go too much into the details, but to sort of illustrate how it works, envisage that you're trying to extract book-author relationships from, say, the internet, for example. So what you do is you start at the top left-hand corner, and you say, okay, I'm going to give a positive example. I'm going to say, J.K. Rowling, Harry Potter. And we entered that, and what we do is we search the whole corpus, which could be the internet or newspapers or scientific documents, and find all sentences that contain those entities. We can then look at the phrases, the context around those entities that relate the two, and from that learn the ways in which we present this particular relationship. And from that, you can find new examples, and the process essentially repeats and repeats, and it's called snowball because you gradually build up more and more examples and more extraction paths. It kind of snowballs out of control eventually, until you've hopefully covered all clever ways of saying that J.K. Rowling wrote Harry Potter. I have finished the implementation of Snowball, and initial results implementing a Snowball stage into ChemDataExtractor have shown upwards of 20% improvements over not the same gold standard that we used in the, because those were chemistry articles, but applying it to a physics corpus, we looked at 20% improvement in precision and something like 10% improvement in F-score, which is quite a significant improvement in a tool that's already pushing the limits in what we can do. So to sort of sum up, ChemDataExtractor is this comprehensive toolkit for extracting chemical information from scientific documents. It presents a very respectable F-score in comparison to other tools. And with further enhancements, it will improve its performance for the other domains in material science. Of course, as we all know, that presents a great opportunity for furthering our understanding in material science research. Thank you very much for listening. Any questions? Yeah, sure, yeah.
Hi, thanks. That was really interesting. And for someone who has no experience so far in text mining, it gives me a good overview of the practical parts of it. Yeah. You mentioned that you needed to have a dictionary of chemistry or something like that to identify the compounds. Is that strictly necessary? And if you were going to move this into a different domain, how would you begin?
That's a fantastic question. So that's kind of talking more about the technical side. So when I say dictionary-based approach, there's a set of abstracts actually taken from PubMed were analyzed and manually annotated to highlight the various different chemical compounds that were in there. And that was used to train an algorithm that learned what essentially made up a chemical compound. And that's supplemented by the full list of chemical compounds, just so we can compare. If it happens to be in the list, then we know it's definitely a chemical compound. So that kind of comes back to named entity recognition, which is the kind of idea of trying to identify specific entities within a subdomain of text. Doing that in a semi-supervised way, you could use a similar algorithm to the snowball algorithm that I talked about just then. You give a few positive examples. With machine learning, you tend to have to give some element of training data, unless you go into the very deep unsupervised learning realm. And then again, you could essentially give a relationship. It could be a single relationship. You provide one example of a chemical compound, and it learns essentially how chemical compounds look in the data. So typically they contain things like internal commas, internal periods, brackets, all these various ways in which we can present compounds. There are other ways, and there are many ways you could apply, and we're certainly looking into that now and seeing what we can do.
So the the use of the term snowball, I assume is because it's the way you often search for information is snowballing. But there is also a project called Snowball Metrics.
Yeah.
Is that just chance that this is the same name?
It is just completely, it's completely chance, really. So the snowball algorithm was actually made in, I think, the year 2000. It's relatively old, and it is based on this idea that you start off with a small number of examples, and it gradually builds up a set of examples in this kind of rolling fashion. So yeah, it is just really chance more than anything else. Yeah.
I was going to say the same. I think I was confused because there's a snowball stemming algorithm,
Yes.
which I think is different from what you have here and so forth. I'd just like to say I think this is very nice work, and I think it looks a very good way of going about it, and hopefully it's moderately generic so it can be translated to other fields, because these tuples, as you call them, are very strong in physical science.
Yes.
Entity, property with qualifiers on.
Yeah. No, exactly. So, yeah, the book-author relation, that kind of binary relation, is quite a simple example. But you're right. In the physical science in particular, we always have this idea: we have a property, melting point, as a compound, a value, and a unit, and that completely defines the relationship. And that's all we need for the database is those exact things. So, yeah, exactly. It's quite strong for the material sciences. Anyway,
So you've got your database of extracted data. What do you do with it then? Is it free for everyone else to use?
Yeah, so that's a very good question. So it comes into this kind of open access availability of data again. So we are currently in the process of setting up our own domain, which will have the repository of all the databases we created. The idea as well is also to publish the data sets there's a new journal, Nature Scientific Data, which primarily focuses on publishing data sets, particularly for validation and these kind of things, which is somewhere we definitely definitely publish the data set, but there's also a requirement for them to make the data completely available in a recognized repository. So yeah, all the data will be completely open access, and there'll be no issues with access at all.
This is great for properties. Does it have any implications for synthesis?
So, ChemDataExtractor, as it currently is, the current build, does have tools for recognizing relations such as synthesis, reactants, solvents, in a similar way to Chemical Tagger and Content Mine can do. So yeah, if whatever particular thing you're interested in, I'd say give it a go, see what you think, and if there's something else you'd like to see added, feel free to let us know, because we're always looking for things to add to ChemDataExtractor. But certainly there are tools for that currently. Yeah.
This might just be a really stupid question, but so if I wanted to use the extractor, do I need to download the software onto my computer and run it from there, or is it run? Where does this happen?
So I'd say if you look at the website, there is an online version. You can use our API on the web interface. Upload a single paper, it will extract all the chemical records. So that's, I think, what most users would use it for, is using it on a single paper. If you want to do a full database generation, I would recommend downloading it to your machine and running it yourself. And that way you have more interaction. You can change various settings and add different extractors and things like that. So there's different ways of interacting with it. There's a command line interface, or you can also use it in an IDE if you want to, all kinds of things. Yeah, and of course it incorporates fully with your own code. So if you want to do things on top of it, you can completely do that, and it's very easy to use.